Okay, in the last lecture, we've seen that the definition of singular transformation. Okay, what is singular transformation? Let T be the linear transformation from V to U. Okay, so if there exists a non-zero x belongs to capital V such that if T of x is equal to 0, okay, the image of non-zero element is 0, then that T is called as, that transformation is called singular transformation. Okay, there exists means at least one element belongs to V. Okay, at least one non-zero element belongs to V such that if their image is 0, then the transformation is called as singular transformation. Okay, and also we've seen that what is the non-singular transformation. What is non-singular transformation? If T is the transformation from V to U. Okay, these are the two vector spaces. It is said to be non-singular if 0 belongs to V, map 0 belongs to V. That is, only element 0 of V. If you take image of that element, then that element 0 belongs to V. Okay, sorry, 0 dash belongs to U. Okay, so what is the singular transfer, non-singular transformation? The only 0 element which maps to 0 of this codomain. Okay, and that is the kernel of T, which is equal to null space of T is equal to what? 0. What is the null space of T? This is the subset of your domain which maps 0 element of your codomain. Okay, so this is the kernel of T is equal to singleton 0. That is the 0 element which maps to 0 of U. Okay, then that transformation is called as non-singular transformation. Okay, so today we will see some three theorems out there. Okay, now look at the first theorem. Okay, statement. Let capital T be a homomorphism. Capital T be a homomorphism of vector space. Vector space V over F. Okay, capital V over F into vector space U over F, capital U over F. Then the set of all those elements, of capital V which corresponds, that is which maps, which corresponds to the zero vector, of capital U under the transformation T, okay, is a subspace, of V over F. What is given to us? T be the homomorphism, vector space homomorphism. That is, T is a linear transformation from V over F to U over F. Then we have to show that the set of all those elements belongs to capital V, which corresponds to the zero vector of U. That means null space of T. Okay. Under T is the subspace of V over F. Okay, what is the meaning of this sentence? Look at here. Then the set of all those elements of V which corresponds to zero vector of U. Okay, suppose this one is V and this one set is U. So this is the zero vector, suppose this one. Okay, now we have to take the collection of those elements from X which maps to this zero element of U. Okay, suppose these are the four elements x1, x2, x, the x4 belongs to V. That is null space of T. Okay, this definition we seen in the previous lecture, in the last lecture. Okay, null space of T is nothing but collection of those elements of your domain which maps to zero element of your codomain. Okay, so you have to show that this null space of T, okay, that is the set of those elements of V which corresponds to zero vector of U is the subspace of V over F. ह्याचा तो subspace असायला हवा. Okay, now look at the proof. Okay, proof. Wait a minute. Okay. So one more statement is there, alternative statement. This statement, this theorem can be asked in the exam like that. Okay. Or if A is a linear transformation. Okay. If capital A is a linear transformation. Capital A is a linear transformation on a vector space V to vector space U. Okay, or W or U. Then show that null space of A. Okay, n of A, that is the null space. Okay, instead of T here, we have taken A's linear transformation. So here, null space of capital A is subspace of V. Okay, so this statement can be asked in the exam like this. Okay, now look at the proof. If you have to show that, you have to prove that one set is the subspace of that vector space. Okay, so there is a necessary condition to show this subspace. Okay, in the last lecture we seen that. Okay, what is the vector space? What is the subspace? Subspace is nothing but subset of that vector space, and itself it is a vector space. Suppose this is V. Okay, is the vector space. Suppose. Okay, and this one, suppose this is the W, which is subset of what? V, and itself it is a vector space. Then what we have? W is subspace. Okay, subspace of vector space V, capital V. Okay, so this is the definition of subspace. Now, look here. Let capital T, okay, be the function or be the transformation from V over F to U over F. Be a linear map. Be a linear map. Let n of T, capital T, denotes, write down all the given things, denote the set of all those elements, of capital V which corresponds to the zero vector of U. capital U. Okay, under the mapping T. Okay, so that what is the definition? From the definition of n of t, n of t is equal to collection of those elements from capital V such that under t the image of x is equal to what? 0. Where 0 is what? 0 element of okay, where 0 denotes the 0 vector. Okay, this 0 vector of the vector space U. Okay, this 0 belongs to what? Codomain. Okay, so what we have? n of t मधले एलिमेंट कोणत्या कुठून येत आहेत? V मधून येत आहेत. So by definition of n of t, okay, n of t, that is null space of t, is the what? Subset of capital V. Is it correct? Okay, so n of t belongs to what? This is the set, where in that set the elements comes from capital V. Okay, such that this condition of t of x is equal to 0. So here the n of t what contained in V, that is subset of V. Now we have to prove that this n of t is a subspace of V over F, and we have to show that first one, the exists element 0 belongs to what? Null space of T. We have to show that this one, null space of T contains 0 element. Okay, and second one, if you have to show that this is the subspace of V over F, that is itself it is a vector space. But by the definition of vector space, you have to show that for all x and y belongs to n of t, okay, and for all a and b, these are the two elements belongs to the field F. This implies ax plus by. Whatever is the element of a, this one, ax plus by, this must be belongs to n of t. Okay, so this is the necessary condition of what? Vector space. X and y belongs to n of t, and a and b belongs to f. It implies, if this implies ax plus by belongs to n of t, then this n of t, automatic, we get this n of t is a subspace, that is vector space. Okay, any doubt up to here? Any doubt up to here? Hello. Okay. So first condition, if you have to show that 0 belongs to n of t. Okay. So first one, by the property of a linear transformation. What we have? T of 0 is equal to what? 0. 0 element must be maps to 0 element. Okay, showing there by 0. Okay, so this 0 belongs to what? n. Okay, म्हणजे हा तुमचा 0 कशामध्ये आहे? Null space of T मध्ये. Okay, image of 0 element must be 0. Why? Write down in the bracket. 0 is equal to what? 0 into u. Okay, u belongs to any vector in V. Okay, so this implies T of capital 0 is equal to what? T of 0 into u. Okay, by the definition of linear transformation, if suppose this is the scalar, so 0 into T of u. Okay, 0 into T of u is equal to 0. Okay, so why we get T of 0 is equal to 0. Okay, so this is u belongs to capital V. Okay, so hence we get hence we get the image of 0 element is what? 0. Okay, so here first condition holds. Now we have to prove that second condition. What is second condition? Look at here. Take any element x and y belongs to n of t. Let x and y, these are the two elements belongs to n of t, and a and b belongs to capital F. B arbitrary element. Arbitrary element का कोणतेही element. Okay, so that hmm, if x belongs to n of t and y belongs to n of t, by the definition of n of t, t of x is equal to what? 0. Okay, x maps to what? 0, and t of y is equal to 0. Okay, now we know that n of t, n of t is what? Subset of vector space V over F, and we have x and y belongs to capital N of t. So this implies what? This is contained in V of F, vector space V over F. So this implies x and y. These are the two elements belongs to V over F. Okay. Then now what is the second condition? Here the x and y belongs to N of t and a and b belongs to capital F. If ax plus by belongs to N of t, then N of t will be the subspace of V over F. So now write down what is A, then T of, find the image of ax plus by. But T is what? Linear transformation. By the linear transformation, we get A into this is T of x plus B into T of y. Okay, so A into this is T of x is equal to what? We have T of x is 0 plus B into T of y is 0. So A into 0, 0 plus B into 0, 0. 0 plus 0 is 0. So this implies T of ax plus by is equal to 0. So image of this element is 0. So this implies a into x plus b into y belongs to what? Null space of T. Okay, hence if x and y belongs to n of t and a and b, okay, for all xy and for all a b belongs to capital F, this implies a into x plus b into y belongs to null space of T. Okay, hence null space of T is what? Subspace. Okay, itself it is a vector space, but it is contained in V. So it is null subspace of V over F. Okay, hence the proof. Any doubt? Okay, what is the theorem? If T is the homomorphism of vector space is nothing but what? Linear transformation. Okay, linear transformation. The another word is for linear transformation is homomorphism vector space. Okay, V over F into vector space U over F, then the set of those elements of V which corresponds to zero vector of U under the mapping T, okay, then it is a subspace of V over F. Okay, this statement can be asked by the in other words. Other words, if A is a linear transformation on a vector space V to a vector space U, then show that N of A is the what null space of T. A is the subspace of V over F or V. Okay, any doubt in this theorem? Reply the काहीतरी. Yes or no? Hello? Any doubt? Okay, so we will move towards the next
No,
point.
sir. No, sir.
The next theorem is range space of a linear map. The next theorem, next theorem, range space. Range space of a linear map. Okay, what is the statement? Look at here. Let capital T be a linear map or linear transformation or vector space homomorphism. Okay, linear map from vector space V over F into a vector space U over F, then range space R of T. Okay, range space is denoted by R of T. In the last lecture, we've seen that this one is a subspace. Is a subspace of what? U over F. Okay, here T is giving from mapping from U to V. Okay, so T of X. Suppose X will be any element of V, then T of X must be belongs to what? U. Okay, the output will be in your codomain. Now we have to show that range space is the subspace of U over F. Okay, now look at the proof. Okay, write down first all given things. We have T is the mapping, is the linear mapping from V over F to U over F. Okay, and by the definition of range space, okay, we denoted it by R of T, which is equal to T of X, such that X belongs to V. Okay, we seen in the last lecture. Okay, or this set can be written as like this. Give this T of X is equal to Y. Okay, Y belongs to this T of X is the element of what? Your codomain, that is Y. Okay, Y belongs to U such that T of X is equal to Y, or Y is equal to T of X for some X. कोणत्या तरी X साठी तो काय T of X is equal to Y for some X belongs to C. So this is your range set, that is range space of linear transformation T. Okay, or T of X be the element of U for all X belongs to V. Now, this element belongs to U. Okay, in R of T, the collection of, look at here in the definition, in the set R of T, is the collection of all the elements of the type T of X. And this T of X belongs to U. And in the R of T, by the definition, T of X, where X belongs to V. So this implies what it implies? The range space of T must be the subset of your codomain. What is your codomain? U. Okay, so here the range space is contained in U. To prove that, we have to prove that range space of T is subspace of U over F. Okay, here we look at here. Suppose this one is U. These are the range of T. Okay, that is subset of U. And we have to show that this R of T is what? Subspace. That means this R of T itself a vector space. Okay, जर तो वेक्टर स्पेस झाला तर तो काय होईल? Subspace of U. Okay, but to prove that R of T is a subspace of U over F, we have to prove that first condition. Okay. Similarly, from the first theorem, here we have to prove that this 0 belongs to range space of T. And the second one, X and Y. These are the two elements from the range space of T. Okay. And A and B, if these are the two elements of the field F. Okay. If it implies AX plus BY belongs to range space of T, then this range of R of T is a subspace of U of F. Okay. Now look at the proof. First condition. What is the first condition? First one. 0 belongs to, by the property of linear transformation, we have by the property of linear transformation. By the property of linear transformation, we have T of 0 is equal to 0. Okay, so this T of 0 is equal to 0, and we have 0 belongs to R of T. Okay, म्हणजे तुमच्या रेंज स्पेस ऑफ टी मध्ये काय आहे? Suppose this 0 belongs to V. This one. Okay, the image of 0 element is what? 0. R 0 कशात मिळेल तुमचा? U. This 0 belongs to U. Codomain. Okay, so here we get there is a image of 0. That is T of 0 is equal to 0. That means this 0 belongs to range space of T. Okay. Write it down once again. So here, by the definition, by the property of linear transformation, 0 maps to 0. Okay. So consequently, we have this 0 belongs to range space of T. Okay, so first condition is hold. Now second condition. What is second condition? Let X and Y. These are the two elements belongs to the range space of T. And small a and small b, these are the two elements belongs to capital F. Okay. Now we have to prove that what? Wait a minute. We have to prove that this one AX plus BY belongs to R of T. Okay. Now let these are the two elements belongs to R of T, and A and B belongs to F. Okay. Suppose this is U. This is R of T. Okay. So here X and Y is there, and this one is V, and T is the mapping from u to v. If suppose x and y belongs to R of t, that means here, so there exists a pre-image such that there existed two elements. Suppose that elements are, suppose this is x dash and this one is y dash. Okay, by the definition of range space of T. Range space of T मध्ये प्रत्येक एलिमेंट कोणत्या टाइपचा असतो? T of x. Okay, so this x is equal to T of x dash for some x dash belongs to V ना, by the definition of range space of T. So एखादा element या R of T मध्ये आहे. If suppose one of the element in R of T, so x is equal to, that element is equal to what? T of x dash for some x dash belongs to V by the definition of R of T. So here we get that exists the element x dash and y dash. Okay. So if x and y belongs to R of T and a and b belongs to the field F, then by the definition there exists x dash and y dash belongs to what? Capital V. Suppose this one is capital V. Okay, there exists a x dash and y dash belongs to capital V, and small a and small b belongs to capital F. Okay, small a and small b belongs to capital F. Instead of writing this one, only write this one. There exists an element x dash and y dash belongs to capital V such that what we have, T of x dash, image of that x dash. Okay, this element is equal to what? X. And image of y dash is equal to what? Y. Okay, give it an equation number 1. Both. Okay, now since what we have, since V is a what? Vector space. Okay, over the field F. And what we have here, this x dash and y dash, these are the two elements belongs to what? V. And we have a and b belongs to field F. That implies V is the vector space. That implies a into x dash plus b into y dash belongs to what? V, capital V. Okay. Now apply the T image of this element. This is the element belongs to V. Why? Since V is vector space. By the definition of vector space, ax dash plus by dash belongs to V. Now apply T on this element ax dash plus by dash. Okay. So the image of हा तुमचा इनपुट कुठे आहे बी मध्ये, मग टी हा कुठे तुमचा आपला अप्लाइंग टी, then this element belongs to range space of T. Okay, so this implies, wait. Okay, so this implies by the definition of linear transformation, what we have, this one, a into T of x dash plus b into T of y dash, this element belongs to range space of T. Okay, but what is T of x dash? T of x dash is a into, look at here, T of x dash is x, T of y dash is equal to y. So this is ax plus by belongs to what? R of T. Okay, hence x and y belongs to R of T and a and b belongs to capital F. This implies ax plus by belongs to what here? R of T. Hence, the range space of T is what? Subspace by the definition of subspace of U over. Okay, any doubt up to here? So here we proved that range space of the linear map. range space of a linear map. That is, let T be a linear map from the vector space V over F into the vector space U over F. Then range space R of T is a subspace of U over F. Okay. So here we see that two theorem. Which one? Suppose this is V. This one is U. So range space. This is the range space is the subspace of U over F. And the null space, that is N of T, is what? Subspace of V over F. Okay, the null space is nothing but kernel of T. Okay, kernel of T is what? Subspace of V over F. Null space of T is subspace of what? V over F. Range space is what? Subspace of U over F. Okay, any doubt up to here? Up to here, any doubt? Okay, so काही डाउट्स असतील तर विचारू शकता. If not, then we are going, okay.
No,
So then
sir.
we are going to move towards the next point, the representation of transformation by matrix, or matrix of a linear transformation, the last topic of our syllabus. Matrix of a linear transformation. Okay, this is the last point of our syllabus. Okay, उद्या हा संपेल. एक्झाम कधी तुमची? एक्झाम कधी आहे? डेट?
So maybe next month.
नेक्स्ट 9 ऑगस्ट असेल. पहा टाइम टेबल आलाय. ओके.
Okay, sir.
Okay. So last point, matrix of a linear transformation. Now, first going to the main topic, first we will see some basic concept. Okay. What is the coordinate vector? Coordinate vector. Coordinate vector. Okay, what is the definition of coordinate vector? Let the set E1, E2, up to so on, En. There are n elements in that set. Okay, be a basis. Be a basis for a vector space. For a vector space capital V over a field K, capital K, for any V, small v, belongs to capital V. There exists a unique scalars. There exists a unique scalars AI belongs to capital K, such that small v, okay, small v belongs to is equal to summation I running from 1 to n AI into EI. Then the coordinate vector of V, okay, to the basis E. Okay, suppose this is the basis E. This is the set E. Okay. The coordinate vector of, what is the meaning of this one? The coordinate vector of V to the basis E is nothing but column vector A1, A2, A3, up to so on, AN. Okay, so what is this one? The coordinate vector of, this is the coordinate vector of V to the basis E. Okay, Look at the once again definition. Let E1, E2 up to so on En be the basis. What is the meaning of basis? This is the basis of the vector space V over K. That means this is the linearly independent set. Okay, this is linearly independent set, and this set spans your whole vector space V. Okay, suppose this is the set S. So linear span of S is equal to vector space. Any vectors belongs to V, we can write in the linear combination of elements of S. Okay, example घेतल्यानंतर व्यवस्थित समजेल तुम्हाला. Okay, so this is the definition of coordinate vector. If E1, E2 up to so on En be a basis of the vector space V over the field K, so any element, okay, any, look at here, any V belongs to capital V. कोणताही वेक्टर तुमचा V मधला, we can write in the form of linear combination of that basis. Okay, look at here. हा basis आहे म्हणजे हा तुमचा linear combination. Okay, याचा अर्थ काय? A1 run this summation E1 plus now I is equal to A2 E2 up to so on En En. आणि हे सगळे कोएफिशिएंट काय करायचे? A1 A2 up to so on En एका कॉलम वेक्टर मध्ये लिहायचे आणि त्याच वेक्टरला म्हणतो आपण कोऑर्डिनेट वेक्टर. Okay, so any vector V belongs to capital V, we can write in the form of linear combination of vectors of E1, sorry, EI, that is E1, E2 up to so on En, and take that all the coefficients in the one column vector, and that vector is nothing but coordinate vector. Coordinate vector काय म्हणलंय? हे सगळे काय तुमचे A1, A2 हे coordinates आहेत. Okay, कोणाचे coordinates आहेत? This is the coordinate of E1. This is the coordinate of E2. Okay, so write down all the coordinates in the one column vector, and that vector is nothing but coordinate vector of which element? V. Okay, to the basis E. These are the bases. Okay, the basis change केला तर तुमचं coordinate change vector V change होते, म्हणून तुमचं इथे E लिहिलंय. Okay, wait a minute. After taking example, the concept is clear. Okay, En. Wait. So this is the definition of coordinate vector. Okay, now look at here for the example. Example number 1. If suppose V over F is the vector space given by R3 over R. Okay, and what is the basis? Suppose beta is the basis, B is the basis. Basis given to us. What is E1? First coordinate is order triplet 1 0 0. Second one is 0 1 0. Third one is 0 0 1. Okay, these are this set is linearly independent, and this set spans your whole vector space. Okay, so this is the basis. This is vector space. Now take any vector x belongs to B. Okay, suppose that x is equal to -3, 4, and 7. Okay, so this x we can write in the linear combination of these three vectors. How? Look at here. X is equal to -3, 4, and 7 is equal to A1 into 1 0 0 plus A2 into 0 1 0 plus A3 into 0 0 1. Now what is the value of A1, A2, A3? You have to write A1 is equal to -3 into, okay, 1 0 0 plus what is A2? 4 into 0 1 0 plus this is 7 into 0 0 1. Okay, so the coordinate vector of x to the basis B. Okay, basis is B now. So is what? Write down all the coordinates in one column. -3, 4, and 7. Okay, so this is the coordinate vector of x to the basis p. Now, any doubt? Any doubt now? If you change the basis, okay, इथं जर हे हा एलिमेंट चेंज केला, तुमचा बेसिसचा संदर्भ वेगळा असेल काहीतरी. ओके, सपोज दिस इज द बेसिस 1 1 0 0 1 1 1 0 1. This is also basis. Okay, basis is not unique for any vector space. You know this one. Okay, मग इथे काय येईल 1 1 0 प्लस a2 into 0 1 1. Okay, plus a3 into 1 0 1. मग हे आपल्याला a1 a2 a3 फाइंड आउट करावं लागते. ओके, ते समजण्यासाठी लवकर येण्यासाठी आपण इथे काय घेतलं, स्टँडर्ड ऑर्डर बेसिस घेतलं. त्याला म्हणतो आपण स्टँडर्ड. Okay, if you change the basis, then the coordinates must be changed. Okay, so here the coordinate vector of x, that is minus 3 4 7. Huh. So coordinated vector is what? And the column vector minus 3 4 7. Okay, it is clear now what is the coordinate vector. Okay, now then we come towards our main topic, matrix of a transformation. Write down here. Matrix of a linear transformation. Okay, and this topic we will see in the next lecture. Okay, for today it is sufficient now. उद्या तुमचे एक्झाम्पल 2-3 एक्झाम्पल घेतल्यानंतर हे सिलेबस कव्हर होईल. ओके, एनी डाऊट अप टू हिअर? एनी डाऊट अप टू हिअर? उडता अच्चू गटला कोणी?
No, sir.
Okay, so the remaining part we will see in the next lecture. For today it is sufficient now. Okay, so thank you for the attending the lecture. You can